Today, for the first time since 3I Atlas reappeared from behind the sun, NASA adjusted one of the numbers that has stayed almost completely stable for months. It wasn't a press release. It wasn't an announcement. It arrived as a small modification buried inside an updated orbital solution, a fractional shift in the non-gravitational term used to model the object's motion. A subtle change, a quiet change, but a change that matters. Because once you understand how these models work, you realize that NASA only updates a term like this when the object itself is doing something new. That adjustment is the reason this story begins here. Because a shift in the A2 term, even a tiny one, means the force acting on 3I Atlas is no longer the same force NASA accounted for last week. It means the models must bend to match the behavior. It means the behavior is ahead of the models. For 4 months, the scientific picture of 3I Atlas has been built around stability, a predictable orbit, a consistent deceleration curve, a non-gravitational parameter that barely changed even after perihelion. Despite the oddities in shape and brightness, the motion itself, the thing that tells you the most, stayed calm. Today's update breaks that streak, and the timing of that break is just as important as the break itself, because it arrives exactly as more telescopes regain full view of the object, and just weeks before the sky opens on December 19th. To understand why the adjustment is significant, you need to understand what NASA changed. The A2 term is the component used to describe any acceleration 3I Atlas experiences that is not caused by gravity, typically from jets, outgassing, or mass loss. For an ordinary comet, A2 being non-zero is expected, but 3I Atlas has not looked or behaved like an ordinary comet since it emerged from behind the sun. It lost its tail. It lost its coma. It showed no signs of active jets. Its surface smoothed into something close to a perfect sphere. And yet the model still required an A2 term to match the trajectory. For months, that value remained steady. Today, it moved. Not enough to change the overall path, but enough to signal that the force acting on the object is evolving. Enough to show that the internal structure, surface interaction, or distribution of mass is no longer the same as it was in August and September. Enough to force NASA's models to follow the object instead of guiding it. The adjustment is small, but the implications are not. A non-gravitational term that changes without visible jets means something in the body is shifting. It could be the exposure of a new surface. It could be internal fracturing. It could be a change in rotation state. It could be subtle sublimation hidden beneath a smooth, insulating layer. What it cannot be is nothing. A gravitational model does not update itself. A parameter does not move unless reality pushes it. This is why NASA's revision is important. It confirms that 3I Atlas has entered a new phase, not a dangerous one, not an unstable one, a measurable one. The timing matters for another reason. Models rely on consistent data. When an object spends 6 weeks behind the sun, the gap creates uncertainty. Not because the object is behaving strangely, but because there is no direct observation. When the object returns, scientists compare the predicted path with the actual one. If the match holds, the model is sound. If there's a gap, even a small one, the parameters must be adjusted. The post-blackout comparison is exactly what triggered today's update. The new observations show 3I Atlas, drifting slightly farther from its expected track than the previous model allowed. Not a dramatic drift, a drift measured in fractions, but a drift consistent across multiple observational teams. And because gravitational influences alone could not explain that drift, NASA increased the A2 value to match the new data. This is the quiet part of orbital mechanics. Numbers move because something real is moving. Today's shift does not indicate risk. It indicates activity. The subtle kind, the internal kind, the kind you don't see in a photograph but detect in motion. And in the case of 3I Atlas, activity without visible jets is already one of the central mysteries. When it first returned from behind the sun, images from amateur astronomers, university observatories, and Tianwen-1 showed an object cleaner and smoother than any comet its size should be. No debris field, no asymmetric glow, no clear sign of mass loss. The sphere-like shape made a strong case that the surface had sealed in some way, perhaps through melting and refreezing, perhaps through fragmentation and reattachment, perhaps through a process we don't fully understand. If that smooth surface is insulating active material beneath it, the non-gravitational effects could shift gradually without producing a visible jet. That is one hypothesis. Another is that the interior of 3I Atlas is rebalancing as it rotates, redistributing mass in ways that affect motion but not brightness. A third is that the orientation of the object has changed, allowing dormant areas to receive new sunlight. There are many possibilities. What matters for now is this. NASA's update confirms that something physical is evolving. The key word is evolving, not exploding, not fracturing, not destabilizing, evolving. And evolution is exactly what astronomers expect from interstellar objects. Their surfaces are ancient, their structures are complex, their responses to solar heating can be subtle and unpredictable. What makes 3I Atlas unusual is not that it is changing, but how it is changing and how consistently its anomalies line up across independent data sets. Today's update is another alignment, another data point, another confirmation that the story is still in motion. It also sets the stage for the observations coming in December. When the object reaches its next optimal viewing window on the 19th, telescopes will measure its brightness, shape, rotation, and motion with more precision than at any time since July. And because the A2 term shifted today, those measurements may reveal whether the trend continues, stabilizes, or reverses. This is why tonight matters. Not because something dramatic happened, but because something measurable did. A tiny shift that keeps the puzzle honest. A quiet signal that the object is still teaching, still responding, still alive in the scientific sense of the word. NASA quietly moved the goalposts today, and now the question becomes, what kind of object forces you to adjust the numbers even when it shows no signs of activity at all? Before you can understand why today's tiny change in the numbers matters so much, you need to understand what 3I Atlas actually is underneath all the anomalies. Not a random comet, not a simple ball of ice. At its most honest level, it behaves like the compressed heart of a shattered world, a survivor core drifting alone between stars. Forget for a moment the smooth green sphere it briefly became, the missing tail, the strange light curve, the invisible push. Strip it back to the kind of object that could generate all of those behaviors without falling apart. What you're left with is not a loose snowball, but the remnant of a moon or planetoid that once orbited a young, violent star. A piece of interior torn free and thrown outward, dense enough to endure everything that happened next. Picture that core as something forged, not assembled. Layer by layer, over hundreds of millions of years, gravity squeezed it inward. The surface you see now would have started deep beneath a crust and mantle long since stripped away. Under that forgotten shell, pressure fractured rock and ice into interlocking plates, welded together by heat and time. It is the kind of structure that can be broken, but not easily erased. If you could stand on it, you can't, but imagine, you wouldn't find a smooth, friendly landscape. You'd see frozen cliffs split by canyon-like fractures, valleys glazed in hard ice, ridges where rock and frozen volatile material have fused together. You'd see bands where stone and ice trade places, the signature of ancient hydrothermal veins that once carried heat and minerals through a young world. It would look less like a pristine comet and more like the exposed root of a planet that never finished becoming one. That kind of structure doesn't form in quiet. It forms in a system where gravity is constantly pulling worlds apart and shoving them back together. A young binary star system is a good candidate. Two suns orbiting each other, their combined tides stretching everything around them. In a place like that, orbits are not stable for long. Moons drift too close. Planets migrate inward and outward. One bad encounter is enough to peel a world like an orange. Crust and mantle flung away. Only the hardest, densest portion left to survive. A fragment like 3I Atlas could have been torn from such a world during a close pass, stripped down to its inner core and hurled into interstellar space. The lighter material evaporates or disperses. The fragile parts go first. What remains is the compressed center, the region that has learned to survive pressure. That is the part that can endure a near pass with a star, a long journey through cold, and then another encounter with a new solar system without disintegrating. This is why cores last when everything else fails. The outer shell of a young world is porous, rich with loosely bound ice and dust. It can be boiled away, ablated, shredded by tides. But the interior is different. It is packed, interlocked, capable of shrugging off insults that would tear a more fragile body apart. When that kind of object passes by our sun, you should expect it to hold together in ways a normal comet might not. You should expect it to be tough. When you understand 3I Atlas as a survivor core, today's new behavior stops looking like a random glitch and starts looking like the latest chapter in a long physical story. A dense, layered object can shift internally without putting on a bright show. Cracks can open beneath the surface. Frozen pockets can thaw and refreeze. Mass can redistribute as it rotates. All of that can change the way it moves, even if the outside remains deceptively quiet. That's what makes this kind of fragment so valuable. It is a time capsule, but not the kind filled with artifacts. Its very structure is the record. Each fracture records a stress. Each seam of frozen mineral marks where fluids once moved. Each welded layer tells you about temperatures and pressures that existed in another system, under another star, in an age our own sun never saw. When you measure 3I Atlas, you're not just measuring an object, you're reading a history written in stone and ice. Seen this way, 3I Atlas isn't a strange intruder passing through your neighborhood, asking to be feared. It's physical evidence that planets and moons form, break, and scatter far beyond the small sample of our own system. It says that worlds elsewhere have been torn apart, and that their remains travel on for millions of years, crossing empty light years before accidentally passing through someone else's sky. The universe doesn't file away its past neatly. It leaves pieces of it drifting. Even broken worlds leave stories behind. A fragment like this carries that story farther than any intact planet ever could. Planets stay leashed to their stars. Cores like 3I Atlas do not. They wander. They encode the physics of violent systems and deliver it across interstellar space. When one of them finally passes close enough to study, the correct response is not dread. It's attention, and that attention pays off. Because once you accept that 3I Atlas is the hardened heart of a dead world, details that seem bizarre start to line up. Its ability to survive perihelion without shedding obvious debris. Its tendency to maintain coherence when a looser comet might fragment. Its capacity for subtle internal change that shows up in motion before it shows up in brightness. None of these are signs of something unnatural. They are signs of something tough. When you think of it as a survivor core, today's updated non-gravitational term feels less like a shock and more like a reminder that this object has been adapting to stress since long before it arrived here. That the same resilience that kept it together when its parent world was torn apart is now allowing it to change quietly under our sun. That what you're seeing now is not the birth of its story, but the latest revision in a long series of adjustments stretching back to another system entirely. This is not a visitor. It's a survivor. And because it's a survivor, you should expect it to do what it has always done. Respond to forces, endure them, and carry the memory in its structure. That's what makes every new measurement meaningful. That's why a small update from NASA matters. It's not just a number changing. It's a confirmation that the core of a broken world is still, even now, reacting to the environment around it. Knowing this gives weight to everything else in the story. It turns 3I Atlas from a weird comet into a physical relic of a process you don't often get to see. It turns an anomaly into context, and it sets the stage for what comes next. Because for all its ancient resilience, for all its hardened layers and scars, nothing about this survivor prepared anyone for how ordinary it looked at first sight in our sky. And yet, for all its history, nothing about this core prepared us for what we saw in July and August. Before the object slipped behind the sun and returned as something no one expected, it behaved with a kind of perfect normalcy that almost felt reassuring. In July and August, if you had pointed a telescope at 3I Atlas and known nothing about its interstellar origin, you would have assumed you were watching one of the most standard comets of the year. Everything about it matched the handbook. Everything looked familiar. Everything made sense. The first hints came from Hubble. Its early images showed a classic structure, a broad coma expanding outward in a soft halo, and a steady, well-defined dust tail trailing behind it. The glow carried the exact spectral fingerprints you would expect from a comet made of Chi-Chon compounds: carbon, hydrogen, oxygen, nitrogen. The same basic chemistry that builds most icy bodies wandering the outer regions of our solar system. Nothing exotic, Nothing alarming. Nothing that suggested a core from a destroyed world or a survivor of tidal violence. Under Hubble's lens, 3I Atlas looked almost calm. That same normalcy showed up in the stereo measurements. As it moved closer to the sun, instruments detected the textbook signature of gas jets, the kind that erupt when solar heating begins to sublimate frozen material near the surface. These jets pointed exactly where they should, back toward the sun, driven by simple thermodynamics. They intensified at precisely the rate expected as the object dipped deeper into the warming region of its trajectory. No strange angles. No unexpected thrust. Just the predictable push of outgassing that every active comet undergoes when it approaches perihelion. The consistency didn't stop with space-based instruments. Amateur astronomers across North America, Europe, and East Asia began posting backyard images of the object. Many of those images were modest. Small telescopes, long exposure stacks, imperfect tracking. But the result was always the same. Their pictures showed the same coma size, the same dust tail orientation, the same steady brightening curve. For an interstellar object, this level of agreement across equipment, geography, and skill level was unusual. Interstellar objects often behave erratically. They tumble, they flare, they shed material unpredictably. 3I Atlas did none of that. It behaved with the steadiness of a comet that had been orbiting our sun for centuries. Even the early light curves supported that idea. Photometric measurements from observatories and amateurs showed a clean, single peak repeating with remarkable consistency. A single peak usually indicates a solid, monolithic nucleus, not a cluster of fragments, not a contact binary, not a loose rubble pile. The rotation appeared stable. The internal structure seemed simple. The light curve whispered one message over and over. This object is whole. Orbit calculations painted the same picture. As more measurements were added, the predicted path grew increasingly precise. The line fit the sky almost perfectly. Day by day, the models tightened until the predicted position and the observed position matched within fractions of an arc minute. It was the kind of accuracy astronomers dream of, a reliable, mathematically cooperative object. When you simulate a comet's motion, and it does exactly what it is supposed to do, you relax, you settle in. In those weeks, nothing about 3I Atlas hinted at what would happen later. There was no warning sign hiding in the numbers, no subtle deviation in the way it reflected light, no drift that suggested deeper changes were forming beneath the surface. If you saw it then, you'd think nothing of it. You would have glanced at its coma, admired the color, noted the clean jet signatures, and moved on. To Hubble, to stereo, to backyard telescopes, to every instrument pointed at it, 3I Atlas appeared to be one of the most straightforward comets of the year. That was the strange part, although nobody realized it at the time. For a moment, we forgot it was interstellar. We forgot it came from another system entirely. We forgot that no one knew what forces shaped it before it arrived. Because everything it did in July and August made it look like a local. And that sense of familiarity created a baseline, a clean, sturdy foundation that made the later transformation all the more dramatic. The contrast between the comet of July and the object that reappeared after perihelion in late September is what gives the story its shape. A story like this needs a calm beginning, so the tension has something to push against. And in July and August, 3I Atlas gave us exactly that. A perfect example of what a comet should look like before it enters the sun's blind spot. That's why the normalcy mattered. It wasn't boring. It was the control sample, the version of the object that everything else would be measured against. And then, the sun took it from our view. As steady and predictable as 3I Atlas seemed in July and August, everything about its story shifted the moment it entered the region no telescope on Earth can penetrate. A blackout, a geometric silence, a perfect alignment where our planet, the sun, and the object fell into a straight line. Earth, Sun, 3I Atlas, blocking every instrument, every camera, every eye that might have watched what came next. Explaining this blackout is simple. When an object passes directly behind the sun from our point of view, the glare becomes absolute. Light from the sun swallows everything around it. Even the most advanced coronagraphs can only mask so much. This region, tightly wrapped around the solar disk, becomes a blind spot where small objects vanish completely. They don't dim. They don't blur. They are erased from sight. That is exactly where 3I Atlas was headed, and the timing couldn't have been more inconvenient. Because the blackout didn't happen during a quiet part of its orbit. It happened at the moment when the object was reaching perihelion, the point of highest temperature, highest stress, highest activity. For a normal comet, perihelion is the main event. It's when jets roar to life, when surface layers rupture, when brightness spikes dramatically, when the nucleus sheds mass in spectacular arcs of dust and gas. If a comet is going to split, fracture, flare, or reshape itself, perihelion is when it happens. But this time, at the one moment when a comet should be at its most expressive, 3I Atlas slipped behind the sun and into silence. No telescope on Earth could follow. No ground-based observatory could track its shape or brightness. Even NASA's space observatories had limited visibility. Some blocked entirely. Some reduced to low-resolution, solar-facing instruments. We missed everything. The most important hours of its journey. The precise window where changes, if they happened, would have happened fast. And scientists knew it. As Dr. Carl Battams from the Naval Research Lab put it, we lost sight exactly when activity should peak. In those hours, instruments recorded nothing meaningful. No images, no detailed photometry, no light curve, no high-resolution telemetry. The story simply cut to black. And when you think about it, that blackout is more than an observational inconvenience. It's a reminder of how the universe works. The things we most want to witness, the transformations, the stresses, the breakpoints, often happen at the exact moment we cannot watch. Not because the universe is hiding from us, but because our vantage point is limited. Our instruments depend on geometry, and geometry is not always kind. There's a quiet philosophy buried in this. The universe hides its most interesting moments. For 3I Atlas, those hidden moments stretched across nearly 6 weeks, a span in which the object was cooked by solar radiation, forced through extreme thermal gradients, and subjected to stresses strong enough to fracture lesser bodies. Comets normally brighten, fracture, deform, shed material, or even evaporate during this stage. But with 3I Atlas, nobody saw any of it. Every camera went blind. Every model had to wait. Every scientist watched the sunlit silence on their screens, knowing the object was there, just unreachable. During this blackout, all anyone could do was wait for the geometry to shift. Wait for Earth to move enough around its orbit for the sun to slide away from the line of sight. Wait for the sky to return the object to human observation. And then, slowly, day by day, the line shifted. The object began its crawl back into the visible sky. Telescopes prepared. Observatories recalibrated. Amateurs waited for clear nights. Everyone expected a comet transformed by perihelion. Maybe brighter, maybe fractured, maybe shedding more dust, maybe showing new jets. The usual possibilities were all on the table. None of them were strange. None of them would have shocked anyone. But that is not what returned. The first images didn't show a flaring comet. They didn't show a fan-shaped spray of dust. They didn't show a distorted nucleus or ragged tail. What came back into view was something no one expected. A shape so clean it looked artificial. A surface so smooth it erased the chaos of perihelion. A body so different from what disappeared that scientists checked their equipment to make sure they were looking at the same object. The blackout mattered because it created a gap, a missing chapter, between the ordinary comet that went in and the transformed object that came out. A gap the universe filled with silence. A gap that forced scientists to accept that the most dramatic moment of the story is the one we will never see. And yet, when the object returned, the mystery deepened instead of resolving. Because what came back was something no one expected. When 3I Atlas finally slipped out from behind the sun, the first people to see it were not NASA teams, not ESA analysts, not the scientists who had been modeling its orbit for months. It was the amateurs, the backyard astronomers, the sky watchers who stay awake on cold nights, stacking exposures, polishing mirrors, and chasing faint smudges across the sky. And the very first report did not come from a major observatory. It came from a man in Wales. He was standing in his small garden on a night just clear enough to bother setting up equipment. A faint coastal wind. Temperatures low enough that breath fogged the air. He aligned his mount, tightened the clamps, and pointed his modest telescope toward the coordinates where 3I Atlas was expected to reappear. He took a long exposure, then another, then 20 more, stacking them the way amateurs do to coax clarity from darkness. But when he processed the images, something was wrong. Or at least it looked wrong. There was no tail, no fan of dust, no coma. Just a single, sharply defined sphere, bright, round, and unmistakably green. He assumed it was a processing artifact. Maybe collimation was off. Maybe tracking slipped. Maybe the stacking software misaligned the frames. So he tried again, and again, and again. Every result was identical. A clean circle, a mathematically neat shape, a comet that did not look like a comet. He uploaded the image to an astronomy forum with a short caption, checking if anyone else sees this. His tone was cautious, almost apologetic, as if he already expected someone to reply with the fix he had missed. But what followed was not correction. It was confirmation. Within an hour, images began flooding in from around the world. Toronto, Osaka, Madrid, the school observatory in Maine, a backyard setup in Idaho, a CCD rig outside Melbourne. Different telescopes, different cameras, DSLR, CCD, CMOS, different filters, different tracking systems, different atmospheric conditions, but the object looked the same in every single image. A sphere, perfectly round, not stretched, not blurred by motion, not smeared into a tail, just a clean circle, glowing a soft green that matched Chan chemistry, but lacked every structural feature expected after perihelion. Observers immediately started troubleshooting, checking collimation, checking guiding logs, checking filters and focus, checking sky conditions and sensor noise patterns, checking star shapes to rule out tracking errors. Every test gave the same answer. The equipment was fine. The sky was telling the truth. It's really a sphere. Then came the measurement from Maine, the school observatory with a surprisingly capable setup. A student team measured brightness across the disk, scraping pixel data to verify uniformity. They found that the brightness varied by only about 3% across the entire visible surface. For the viewer, that level of uniformity is unheard of for a post-perihelion comet. Objects that survive perihelion typically emerge ragged, uneven surfaces, jets, pockets of sublimation, newly exposed ice, debris fields. They are asymmetrical, chaotic, shedding material. Their brightness maps show variation everywhere, but not this. This was smooth, too smooth, and the absence of cometary signatures was absolute. No dust tail, no coma halo, no jets, no debris trailing behind it. Even with long exposures, nothing streaked beyond the spherical boundary. The object was simply clean. By this point, the amateur community was in full conversation mode, comparing notes, sharing calibration files, double-checking coordinate logs. What made the situation even stranger was that none of the usual explanations fit. Jets don't vanish this completely. Comas don't collapse into perfect geometry. Tails don't disappear instantly. Perihelion does not polish an object into a sphere. And then, after the wave of amateur uploads, the professional observatories quietly checked their own reserves of data. Some of them had captured low-cadence telemetry of the region after blackout. Some had partial resolution readings. And all of them saw the same thing: a sphere, not a fuzzy nucleus, not a cloud of fragments, a sphere. NASA teams ran internal verifications. ESA analysts compared the new signatures to older baselines. Ground-based observatories aligned timestamps to see if the object showed any hint of deformation. Nothing. Every dataset pointed to the same shape: a perfectly smooth, single-body, green-lit sphere. They chose not to release a statement immediately, not because they doubted the data, but because extraordinary uniformity demands extraordinary certainty. Meanwhile, two spacecraft, MRO and China's Tianwen-1, offered the first higher confidence confirmations. MRO, though not designed to image deep space objects, managed to capture enough contrast to confirm the lack of visible jets or significant debris fields. The silhouette matched what amateurs were seeing: round, concentrated, self-contained. Tianwen-1 moved quickly. Their team released images earlier than expected. Those pictures, too, showed a clean sphere with no tail, no coma, no plume signatures. For viewers, especially U40+ men who have seen countless CGI renderings online, this was clarifying. This was not CGI, not a simulation, not processed artistry. These were raw captures from a variety of platforms, cross-checked across continents, sensors, and teams. The sky was the consistent source, and consistency is the gold standard in astronomy. This was the moment when the community, amateur and professional, aligned. A comet had gone behind the sun, and it had come back as something else. A perfectly smooth green sphere that shouldn't exist. Not fractured, not darkened, not brightened into a dust storm, but reshaped in a way nothing in cometary physics predicts. Even seasoned researchers reacted with disbelief. Dr. Jessica Agarwal said it plainly. Comets don't just decide to turn into spheres after perihelion. And Dr. Paul Byrne added the sentiment every skywatcher felt. If your images and my images and their images all show the same sphere, you have to start trusting the sky. This was the first major break in the story. The first moment where the familiar structure of a comet gave way to something no textbook had prepared anyone for. The first time the object's interstellar origin felt real again. But the shape was only half of the problem. The way it moved was the other half. When the first images of the spherical 3I atlas circulated, the visual shock alone was enough to stir the astronomy community. A comet that returns from behind the sun as a perfect green sphere is already unusual. But sometimes photographs tell only half the story. To understand whether an object has truly changed, you don't just look at it. You measure how its brightness behaves as it spins. That behavior is captured in something deceptively simple: the light curve. For anyone listening who isn't familiar, a light curve is the record of an object's brightness over time. When a rotating body has a shape that isn't perfectly symmetrical, or if one side reflects sunlight differently than the other, the brightness rises and falls as it spins. Plot that rise and fall on a graph, and you get a pattern. That pattern is the light curve. A single peak per rotation usually means one major bright spot, or one dominant asymmetry in the object's shape. Maybe a jet, maybe a reflective region, maybe a slightly elongated nucleus. But it's simple, predictable. One rotation, one brightness peak. 2 peaks per rotation are different. 2 peaks mean 2 distinct reflective regions, or 2 shape-driven variations, or, in some cases, 2 bodies very close together acting like one. It means something inside or on the surface has changed in a physical, measurable way. Before perihelion, 3I Atlas behaved like a dream. Its light curve was almost boring in its consistency. One clean peak, a perfect rhythm, no noise, no irregular bumps, no hint of structural complexity. You could look at its curve and almost hear the implied message: I am a sturdy, single-bodied comet doing exactly what I'm supposed to. But after it returned, after the sphere appeared, photometry teams around the world began stacking their new data. And what they saw was the first deep confirmation that the transformation was not cosmetic. It was physical. When they fit the new observations into a curve, the graph didn't show a single peak anymore. It showed 2. 2 brightness highs for each rotation cycle. Imagine the chart in your mind. Before, 1 rise, 1 fall. After, rise, fall, rise again, fall again. A shift like that, within a matter of weeks, is not trivial. It means the object did not simply look different. It was different. From a scientific standpoint, a double-peaked curve could mean several things. A more elongated shape, something slightly stretched, more like a dumbbell than a sphere. Not wildly distorted, but no longer the perfect circle early images implied. 2 distinct albedo regions, areas of different reflectivity on the surface, possibly patches of newly exposed material created during perihelion. 2 active zones, not jets, none were seen. but regions responding differently to solar heating. Or, the most dramatic interpretation, two closely bound cores, perhaps partially split, but still gravitationally tied. Nothing in the new data pointed to a catastrophic fragmentation, but everything suggested that the internal configuration had changed. And importantly, the sphere was no longer perfectly spherical. Careful stacking revealed the faintest hint of elongation, a whisper of asymmetry that matched the new light curve. Not two bodies drifting apart, but not one seamless body either. A subtle evolution, a rebalancing, a change in the interior translated into a change in the way it reflected sunlight. This matters because light curves don't lie. As Dr. David Jewett from UCLA put it, light curves don't lie. When they change, something physical has changed. And Dr. Karen Meach, one of the most respected observers of interstellar objects, summarized it even more sharply. We're not just seeing a different angle. We're seeing a different object. Those words echoed through every observing team. If the light curve changed, the structure changed. And if the structure changed, something happened to 3I Atlas behind the sun, during the very blackout when we couldn't see it. The key here is perspective. Astronomy is full of illusions: viewing angle, exposure time, dust interference. But light curves cut through illusions. They measure behavior, not appearance. And behavior is data. Before perihelion, one peak, one nucleus, one simple rotation, one textbook solution. After the sphere appeared, two peaks, a more complex body, a more complex rotation. The first undeniable proof that the object had physically altered itself. And yet, even as the structure shifted, the community could say confidently, there was no scenario, none, that suggested any danger to Earth. No incoming trajectory, no hidden threat, no chaotic fragment spraying dust in unpredictable directions. Every hypothesis stayed within the boundaries of physics and safety. The object was evolving itself, not moving toward us. Still, something about the timing unsettled scientists in the best, most curious way. Because internal changes are one thing, expected even, for an object under extreme heat. But what made the situation stranger was that these internal shifts didn't remain internal. They reached outward into the very path of the object, somehow, without jets, without bright activity, without visible thrust. The orbital models needed adjusting. The trajectory had drifted, subtly, precisely, consistently. And that raised a new question. If the object was no longer shaped the same, and no longer reflecting light the same, why was it also no longer moving the same? One peak became two. That's not cosmetic. That's structural. And when structure changes, motion can change too. Which brings us to the next mystery, the one that pushed every model to its limit. But even stranger than its changing light was the way its path refused to obey gravity alone. If the sphere was the first sign that 3I Atlas was no longer behaving like its July and August self, what came next was even harder to ignore. Because this time, the strangeness wasn't in how it looked, but in how it moved. And motion is math. Motion leaves fingerprints. Motion doesn't lie. To understand what happened, you need to know one simple truth about comets. They are messy travelers. As they approach the sun, frozen material begins to sublimate, turning ice directly into gas. That gas sprays outward through cracks or vents on the surface, and every spray acts like a tiny thruster. Not enough to steer a comet like a spacecraft, but enough to nudge its trajectory ever so slightly. Astronomers expect this. They even model it. The little jets create what scientists call non-gravitational acceleration, a tiny push that adds or subtracts speed along the comet's path. And because this push tends to point away from the sun, it usually helps explain why comets sometimes deviate from purely gravitational, perfectly Keplerian orbits. This push is represented by a parameter called A2, the non-gravitational term acting tangential to the orbit. For normal comets, A20 is standard. Jets make sure of that. But here's where the problem began. After perihelion, when 3I Atlas came back into view as a perfect sphere with no tail, no coma, no jets, no dust, no visible mass loss whatsoever, A2 should have dropped towards 0. With no jets, there should be no push, no thruster effect, nothing to accelerate it, except the data didn't agree. Teams at Harvard, JPL, ESA, and multiple observatories began fitting their post-blackout measurements into new orbit models. They used over 1,000 data points: Hubble, stereo, ALMA, MRO, ground-based telescopes, amateur measurements, radar constraints. They threw everything at the models. And every single time, the fit refused to close unless they included an A2 term that was distinctly, stubbornly non-zero. Even stranger, A2 showed up consistently across different instruments, across different nights, across different teams, across different continents. Noise doesn't do that. Sensor errors don't do that. Bad tracking doesn't do that. But physical forces do. The problem was simple and infuriating. There was a measurable push, but no visible source for it. The best way to understand how bizarre this is might be with something more familiar. Imagine standing by a pool table, watching a cue ball glide across what you believe is a perfectly flat surface. For the first few seconds, it moves straight. Then, without warning, it begins curving. Not once, not randomly, but consistently, always bending the same direction, again and again, even when you strike it from different angles. You check the table. No slope, no imperfections, no magnets, no gusts of air, no trick. The ball just curves. That is the A2 problem with 3I Atlas. If something is pushing it, we should see the push, but we don't. Scientists began eliminating the usual explanations. Solar radiation pressure? Too weak by an order of magnitude. It can move dust, not a compressed planetary core. Fragmentation mass loss? Impossible. Fragmentation produces debris. Clouds, streaks, particles scattering sunlight. Long exposures show nothing. Absolutely nothing. Random sublimation pockets? Those leave surface hotspots, tiny fans of dust, irregular brightness patterns. 3I Atlas shows none. Its surface is smoother than most asteroids. With every easy explanation removed, what remained was the unsettling part. The force was not only real, it was consistent. Photometry and astrometry revealed that the push stayed stable over multiple rotations, pointed slightly sunward instead of away, opposite of typical jets, did not flip direction even when the object turned, produced a smooth, predictable deviation in the orbit. Jets usually spin with the body. They flicker. They pulse. They create noise. This was none of that. This was something else. Something steady. Something persistent. Something the object was doing, but not showing. This is where caution matters. It's tempting. Too tempting to jump to exotic conclusions. But the role of science is not to panic. The role of science is to measure, so the narrative stays grounded. No talk of engines, no talk of machinery, no dramatics, just physics. A force exists. We can measure it. We cannot see it. Not yet. Dr. Marco Micheli from ESA captured this sentiment perfectly. We are seeing non-gravitational acceleration without the usual smoking gun. And from Dr. Avi Loeb, whose team fit multiple versions of the orbit. If you need 10% mass loss to fit the curve, you should see 10% of the mass somewhere. We don't. That quote became a pivot point because it framed the problem with brutal clarity. If 3I Atlas were losing mass at the rate implied by the A2 term, the sky should be filled with evidence: dust, jets, irregular brightness. Instead, we see a sphere so clean it looks polished, which means one thing: the force is real, but the mechanism is invisible. And here is the most important part for you, the viewer who's been following this journey carefully. You now understand something only a small slice of the public understands. This isn't just weird behavior. This is a measurable, physical deviation that refuses to fit the patterns of ordinary comets. A textbook comet turns into a sphere. A single-peaked light curve becomes double-peaked. And now, an object with no jets is being subtly pushed by something we cannot yet identify. All of this leads to the next chapter, the part that surprised even veteran orbital dynamicists. Because when you take this invisible push and you run the simulations forward and you let the numbers draw the line through our solar system, the path it creates becomes even stranger. And when you run the clock forward with that invisible push, the path it draws through our solar system becomes even stranger. By the time scientists accepted that 3I Atlas was being pushed by a force no one could see and shaped by a process no one had watched, there was still one more layer of strangeness waiting beneath the surface. Because in astronomy, it's not enough to ask what an object looks like or how it rotates. Eventually, the question becomes, where is it going? And with 3I Atlas, that question produced one of the most mathematically unusual results in modern orbital analysis. A path through our solar system so clean, so uncommonly smooth, that even the most conservative teams had to admit, this is not the typical comet we're used to modeling. To understand why, you need to picture how orbital simulations actually work. When an object enters the solar system, observatories collect positional measurements, tiny snapshots in time marking exactly where it was against the background stars. Then groups like Harvard, ESA, and JPL take those measurements and run simulations. Not dozens, not hundreds, hundreds of thousands, sometimes millions. Each simulation adjusts the initial conditions slightly, nudging the speed, the angle, the position, the rotation state. It's like taking a handful of dice, shaking them, and rolling again and again to see how many outcomes resemble the object's real-world path. For most comets, the distribution is broad. Random comets scatter across the simulation space like buckshot, a spectrum of trajectories that differ wildly in angle, plane, and distance from the inner planets. A typical interstellar comet, even more chaotic. Most would overshoot the ecliptic altogether, or slice through the solar system at steep angles. That's what the models predicted for 3I Atlas. That's what everyone expected. But that is not what the object actually did. When the Harvard and ESA teams ran their simulations, something strange emerged in the statistics. Out of tens of thousands of trajectories generated, only a tiny fraction resembled the real path of 3I Atlas. ESA calculated the probability, 0.06%. That means that if you ran the same simulation 100,000 times, only about 6 outcomes would look like the graceful, quietly efficient path 3I Atlas actually took. Dr. Jonathan McDowell put it plainly. If you ran the simulation 1,000,000 times, you wouldn't expect this as your default outcome. For the viewer, for the U40 plus mind that loves patterns, here's a simpler way to imagine it. Imagine rolling a ball down a mountain and having it land on the same narrow ledge 3 planets in a row, by accident. That's how strange this trajectory is. Not impossible, not miraculous. Just statistically unlikely. And the surprises didn't stop there. 3I Atlas didn't just pass through the inner solar system. It passed through it with an attentive sort of efficiency. Its flyby distances were just enough everywhere. Mars, close enough for crisp imaging from orbiters, far enough to avoid gravitational disruption. Venus, a clean, distant pass, a geometry that lets solar observatories observe without interference. Jupiter's wider influence skirted just outside the region, where the giant planet's gravity could significantly alter its path. Each crossing was threaded like a needle. Near, but not too near. Helpful, but not dramatic. Close enough to observe, but not close enough to distort. And then there was the timing. The timing was the part that made even the calmest orbital dynamicists sit back in their chairs. 3I Atlas entered blackout behind the Sun exactly during perihelion, the period when comets are normally at peak activity. We missed the only hours where a natural comet would have revealed what caused its structural change. Then, as Earth moved just far enough along its orbit, the object emerged into view just as dozens of probes, spacecraft, and observatories happened to be in prime position to detect it. Not intentional, not planned, but difficult to brush off as ordinary coincidence. For anyone listening, here's where we draw the boundary clearly. We are not saying the path was deliberate. We are not saying the trajectory was designed. We are not saying the object chose its encounters. But we are saying that the path it took is unusually efficient. The kind of line you draw only if you were trying not to waste energy or momentum. The phrase scientists used, spoken quietly in conference rooms and email threads, was this: it behaves more like a path that conserves chances and energy than one drawn by random melting. And that's the uncomfortable beauty of it. Because space is chaos, orbital scattering, gravitational kicks, thermal disruption, random perturbations. The universe is messy. The solar system is messier. Comets are the messiest of all. But every now and then, just once in a while, you get a curve so clean it makes you pause. A line through a noisy solar system that shouldn't look this elegant. As Dr. Katie Mack once said, sometimes the math is the first one to tell you that your assumptions are too small. The math wasn't screaming. The math wasn't hinting at danger. The math was simply saying, this path is not the typical product of chance. And in science, when the data is this strange, the next question is never what does the public think? It's how do the agencies respond? Because once you combine a shape that shouldn't exist, a force with no visible source, and a trajectory that threads gravitational gaps with 0.006% probability. It stops being just a scientific puzzle. It becomes something institutions have to deal with. And when orbits start to look this unlikely, agencies don't just watch, they react. By the time 3I Atlas emerged from behind the sun, and the amateur images of the perfect green sphere began circulating online, another set of images already existed. Higher resolution, closer, taken from a vantage point Earth could not match. They came from the Mars Reconnaissance Orbiter. The MRO had captured 3I Atlas during the blackout period, looking outward from Mars's orbit, while Earth was staring directly into the sun. From MRO's angle, the object wasn't hidden. It wasn't lost in the glare. It was right there, small but resolvable, drifting past the inner solar system while Earth observers saw nothing. Those images were transmitted back to JPL in California and the University of Arizona's HiRISE team weeks before the public ever heard a word. And then, nothing happened. NASA held the images for 6 weeks. No release, no statement, no timeline. Not because something was wrong, but because something was uncertain. During that silence, something else happened. China moved first. The Tianwen-1 spacecraft, still operating around Mars, released its own images of 3I Atlas. And those images confirmed exactly what amateurs were saying. A sphere, smooth, green, clean. No tail, no jets, no debris, no fragmentation cloud. For the global astronomy community, this was a jolt. Not because of rivalry, but because the usual order had flipped. People started asking, half joking, half serious, did China just beat NASA to its own sky? And as Tianwen-1's images spread across social media and astronomy forums, the silence from NASA became louder. Some observers wondered gently, is NASA double-checking? Are they waiting for verification? Or is something in the images harder to interpret? The curiosity reached Washington. In a routine committee briefing, a handful of U.S. lawmakers asked NASA for clarification about the delay, not in an accusatory way, but because attention on 3I Atlas had grown globally. When an interstellar object behaves strangely and another nation releases images first, Congress naturally asks questions. Eventually, NASA did release the MRO photography, but they didn't release it raw. They released processed, cleaned, contrast-adjusted versions, the same way they usually do for spacecraft imagery. This is standard practice, but because Tianwen-1 had already shown raw-ish frames, some people had hoped NASA would provide the uncalibrated FITS data. That didn't happen. Still, the result was clear. MRO's images matched everyone else's. A sphere, no jets, no post-perihelion dust. NASA's official explanation focused on calibration pipelines, radiometric cleaning, geometric correction, star field alignment, instrument noise removal. The steps that make spacecraft data reliable. None of this was unusual. Spacecraft images go through a long chain before release, and NASA tends to release only when it is absolutely sure of what it's showing. As Dr. Amy Mainzer from JPL put it, data delays are not cover-ups. They are caution. Meanwhile, another quiet wrinkle appeared. The Pentagon's ARO, the All-Domain Anomaly Resolution Office, briefly added 3I Atlas to its internal watch list, which is a normal part of their job when unusual aerospace-related reports appear. Then, just as quietly, they removed it. No announcement, no explanation. But again, nothing unusual. Objects that have high public visibility sometimes get flagged and later dropped when determined irrelevant to national security. Still, for a public already fascinated by an interstellar visitor, that brief appearance and disappearance added to the sense that the human response to 3I Atlas had become complicated, not conspiratorial, just careful, deliberate, slow. Because when data is strange, agencies do what humans do when confronted with the unfamiliar. They pause, they double-check, they hesitate to speak before the math is certain. In the world of planetary science, silence isn't suspicion. Silence is procedure. And that's the lens this entire sequence needs. NASA wasn't hiding anything. China wasn't revealing anything unusual. ARO wasn't signaling anything dramatic. Each institution was responding according to its own rhythms, shaped by bureaucracy, scientific rigor, and different attitudes toward how quickly data should be public. This is the part of the story that rarely appears in news headlines. The human side of dealing with weird data. A comet becomes a sphere. Its light curve changes. Its orbit refuses to match purely gravitational predictions. Suddenly, every team involved must decide what to publish, when, and how much context they need to add. The silence became part of the story, not because something was being hidden, but because caution slowed the release of information. And that brings us to the next turning point. With images in hand, with photometry logged, with orbit models updated, with agencies caught up, the question shifts from what happened to what does it mean? Now that we have all the images, let's talk about what scientists actually think is happening. By the time every image had been released, every light curve analyzed, every orbital model refitted, the scientific community found itself facing a simple truth. 3I Atlas had changed. Not symbolically, not visually, physically. But change alone doesn't answer anything. It only opens the door to the real work. Building hypotheses, testing them, throwing away the weak ones, and resisting the temptation to jump to the most dramatic explanation just because it sounds exciting on social media. This is the part of the story where science earns its reputation for calm. No panic, no sensationalism, just logic, data, and humility. Here are the leading hypotheses, the ones grounded in physics, not rumor. 1. The planetary core fragment. Hypothesis. This is one of the oldest ideas, and still one of the strongest. It goes back to the structure, the mix of rock-ice composite, the durability, the uniform brightness, and the ability to survive perihelion without shedding visible mass. A planetary core fragment, a hardened piece of a young moon or small world, fits those clues. Deep compression explains the density. Composite layers explain the green Chan glow. A violently stripped world explains why only the interior survived. It matches the kind of interstellar material we rarely get a chance to study up close. It also aligns closely with what many astronomers proposed months earlier. This scenario explains durability and symmetry, but not everything, which is why more hypotheses stay in play. 2. Internal restructuring after perihelion. The light curve tells a simple story. One peak became two. That means something inside shifted. This hypothesis suggests a hollow pocket collapsed. Ice migrated. The internal mass distribution changed. This is the easiest explanation for the new rotation pattern, and it doesn't require the object to split or tear. Think of it like a snow globe inside a furnace. Heat changes the distribution, even if the glass sphere stays intact. Internal restructuring also fits the faint elongation found when photometrists stacked high-precision frames. 3. Early stage fragmentation, but not separation. This idea attempts to explain both the double-peaked light curve and the hint of elongation. Two connected lobes, a dumbbell shape, not fully separated, but no longer one perfect lump either. This would create two brightness sources close enough that amateur telescopes blur them into a single sphere, while high-resolution photometry detects the dual pulses. It doesn't require a dramatic breakup, just a quiet shift. Something subtle enough to happen during the blackout. Early fragmentation also explains why some simulations needed multiple submasses to match the observed rotation drift. 4. The recrystallization shell hypothesis. This hypothesis focuses on the surface, not the interior. When an icy body approaches perihelion, the outer layer can melt microscopically and then refreeze into a smooth, glassy shell as it cools. A real-world analogy exists. Comets sometimes develop crusts, thermal shells hardened by repeated heating cycles. But 3I Atlas may have pushed this to an extreme. Intense perihelion heat, rapid cooling in the shadow of the sun, a moment of phase change, and then a frozen shell that smoothed out previous irregularities. This could explain why the sphere looked too perfect. It was effectively resurfaced. 5. Interstellar ice physics. We haven't seen before. This is the most open-minded yet most conservative hypothesis. It doesn't assume destruction. It doesn't assume restructuring. It simply assumes ignorance. That interstellar ices, processed for millions of years by cosmic rays and deep space conditions, behave in ways our solar system-centric models don't predict. No sci-fi. No engines. No craft. Just ice chemistry we haven't studied enough. Interstellar visitors obey the same physics as everything else, but their initial conditions are wildly different. As Dr. David Jewett put it, interstellar visitors don't owe us familiarity. This hypothesis is the scientific equivalent of saying, let's not pretend our sample size of 2 interstellar objects tells the whole story. The common thread across all hypotheses, without exception, one point is universal. None of them suggest danger to Earth. Not one. Not even remotely. Every explanation circles back to the same core idea. The object is changing itself, not threatening anyone. The weirdness is internal, not directional. This is a puzzle, not a problem. And that separation, the boundary between curiosity and fear, is exactly what keeps the science sober and grounded. Separating science from rumor. This is where we draw a very clean line. 3I Atlas shows no sign of engines, propulsion, artificial control, deliberate steering, or anything resembling designed intent. A mathematically efficient path is not evidence of design. A sphere is not evidence of craft. A non-gravitational term is not evidence of propulsion. A restructure is not evidence of intelligence. The universe produces strange shapes. Heat produces strange changes. Statistical outliers exist, and interstellar material is wildly unfamiliar. As Dr. Michelle Thaler said, unexplained is not the same as unexplainable. Sometimes a mystery is just a point on the curve before the answer. And now, the real question. All these hypotheses are reasonable. All of them fit some of the data. None of them fit all of the data. Not yet. That's why the next key date matters so much. Because on December 19th, the geometry becomes perfect. The distance is ideal. The brightness stabilizes. Multiple spacecraft have clean lines of sight. Ground-based telescopes get their best chance yet. Whatever 3i Atlas is doing, restructuring, fragmenting, recrystallizing, or showing interstellar physics we've never studied. December 19th is the night when the sky finally answers back. And that brings us to the night everyone is waiting for, December 19th. For months, every discussion, every chart, every late-night telescope stream has reached toward a single date, December 19th. Not with fear, not with dread, but with the quiet anticipation of someone waiting for the next page of a story they've been living inside. You've heard the data, you've seen the changes, and now we finally reach the moment when the sky lifts its own curtain and shows us what comes next. So why this night? Why this moment? Why does December 19th matter more than any day before it? 1. Why December 19th is the turning point. December 19th is the first time since the blackout that everything lines up. No sun blocking the view. No geometry issues. No missing hours or blind angles. This is geometry at its cleanest. The kind of alignment astronomers wait entire careers to see. It's also the closest 3i Atlas comes to Earth after its perihelion transformation. Not close in the sense of danger, not remotely. Close in the sense of clarity, in the sense of visibility, in the sense of giving every major instrument on and off Earth the perfect shot. For the first time in months, every telescope, ground-based and space-based, will look at the same object at the same time without interruption. JWST will see the thermal profile. Subaru will map the coma even if it's faint. VLT will chart rotation. ALMA will sniff out molecules even in tiny amounts. And amateurs, hundreds of them, will be streaming their live views, frame by frame, from small backyards across the world. The blackout was silence. December 19th is the reply. 2. The 5 possible outcomes. All safe, all interesting. Not predictions, just possibilities. Each one safe, each one scientifically meaningful. Each one enough to make any space-loving viewer feel like they're watching history unfold. Scenario A. It brightens. Maybe the sun heated deeper layers during perihelion. Maybe trapped gas inside finally reaches the surface. If it brightens, it means internal activity returned. A normal, fascinating, harmless, comet-like behavior. Scenario B. It dims. That would mean the object is calming down, stabilizing after restructuring. A dimmer 3i Atlas is a quieter 3i Atlas, not dying, just cooling. Scenario C, it changes shape again. Another shift, another elongation, another curve in the light data. If this happens, it will tell us which restructuring hypothesis is closest to the truth. Scenario D, it fragments. A peaceful breakup. Nothing dramatic, nothing dangerous, just stress release. 2 small pieces drifting together, like many comet remnants do. Beautiful, predictable, scientifically gold. Scenario E, nothing happens at all. It stays a stable sphere. No brightening, no dimming, no new jets, no fragmentation. This is the scenario many scientists secretly like most. The sign of an object settling into its post-perihelion life. And no matter which of the 5 happens, one truth remains constant. None of these paths intersect Earth's orbit. Not now, not later, not ever in this cycle. Your world stays exactly as it is. Quiet, steady, safe. 3. what December 19th really represents. It's not the drama some corners of the internet whisper about. It's the opposite. It's clarity. December 19th is the moment when the universe gives us the next clue. Not a warning, but a continuation, a data point, a page turn. It's the night when everything we've tracked since July finally speaks with its own voice. Not through pressure, not through fear, just through information. And that's why people across the world will look up with you. From observatories, from fields, from rooftops, from quiet rooms lit only by the glow of a laptop screen. Because the beauty of astronomy has always been this. When something out there changes, we're allowed to change with it, to learn something new, to understand a little more, to feel, if only for a moment, that you are living at the exact right time to witness something rare. You are part of that moment. Whether you own a 14-inch Dobsonian or just curiosity, you are in the small, rare group of people who have followed 3I Atlas close enough to understand why this night matters. Most people will only hear the headlines later. You will have lived the context. For the tone of the night, not fear, not adrenaline, just a calm, steady pulse of anticipation, a night of clarity, a night when telescopes hum, a night when live stream chats scroll slowly with people saying nothing more dramatic than, "Do you see it yet? Is that the brightness curve? Is that new?" A night where the sky isn't loud, just honest. And whatever the first images reveal, whatever the brightness curve says, whatever shape appears in those initial frames, you remain right where you've always been, on a planet that is safe, steady, glowing gently under its own quiet sun. 5. What you can expect. You can expect answers. Not all of them, but the next layer. You can expect clarity. Not perfect, but better. You can expect wonder. The grounded kind, the adult kind, the kind that reminds you why you fell in love with science in the first place. As Dr. Neil deGrasse Tyson says, prediction isn't the goal. Understanding is. And Dr. Brian Cox adds, the sky rarely gives us drama. It gives us perspective. On December 19th, perspective is exactly what we get. A deeper view, a cleaner measurement, a moment where the universe turns to you and says, here is the next piece. And as this chapter closes, there's only one thing left to say. There's a moment after the data, after the diagrams, after the questions, when everything finally settles into something simple. Not an answer, not yet, but a feeling. A steady, grounded, unmistakably human feeling. That's where we are now. And that's where this last chapter begins. Picture 3I Atlas, drifting across a darkness so wide and so clean, it almost feels quiet to look at. The same darkness it has crossed for thousands of years between the stars. The same darkness it will return to long after it passes through our small neighborhood. And picture Earth beneath you, silent, untouched, unchanged. Your room dim, a soft lamp in the corner, the hum of nighttime in the background. Nothing about your world has shifted. Nothing has tilted. Nothing has moved out of place. You are here, steady as ever, listening as an interstellar visitor fades gently into the outer dark. You walked from its ancient origin, the lonely core of a shattered world, to its ordinary July and August behavior, to the blind blackout behind the sun, to its unexpected return as a smooth green sphere, to the way its light curve split into two peaks, to the invisible push shifting its trajectory, to the improbable orbit cutting the solar system with mathematical elegance. to the reactions of NASA, MRO, Tianwen-1, Congress, and Aero, to the 5 scenarios waiting for us on December 19th. You didn't skim headlines. You understood the sequence. You followed the physics. You saw the context. You're ahead of almost everyone else following this story, and you earned that clarity. So let's say this plainly, without drama, without suspense, nothing here threatens Earth. Nothing here points toward danger. Nothing about 3I Atlas intersects our orbit, our future, or our safety. It is a curiosity, not a crisis. A phenomenon, not a problem. A puzzle, not a threat. Whatever happens on December 19th, brightening, dimming, shifting, splitting, or doing absolutely nothing, your world stays exactly as it is. Calm, steady, blue, and whole. Here's the part people forget. You live in a universe that allows you to witness something rare without ever putting you in harm's way. That's a gift. A quiet one. A subtle one. But a gift nonetheless. It is the universe saying, you don't need to fear me to learn from me. You don't need to lie awake to understand me. You don't need to brace for impact to appreciate my mysteries. And that's why this is science not for sleep. Not because it keeps you awake with worry, but because it keeps you awake with clarity, with curiosity, with the grounded confidence that comes from knowing what's real. This wasn't a bedtime story, and yet, somehow, you feel calmer anyway. You understand more now than you did an hour ago. You understand more than most people watching this unfold online. You're not guessing. You're not doom scrolling. You're not lost in rumor. You're centered in knowledge. And knowledge has always been the thing that steadies the mind. As Carl Sagan once said, understanding replaces fear faster than anything else. You're part of this journey, part of this unfolding chapter in the long history of interstellar visitors, part of this rare moment when astronomy feels both intimate and immense. December 19th isn't just a date on a chart. It's a checkpoint for everyone who has followed this story with curiosity instead of fear. When that night arrives, when the first raw images appear, when the live streams begin, when the brightness curve updates, we'll be here to break it down, to make sense of it, to translate data into clarity, to remind you what matters, what doesn't, and what's simply beautiful to observe. No hype, no fear, just grounded, steady perspective, the sleepy universe way. And now, as the final frame fades and the sky goes quiet again, as 3I Atlas drifts into the dark like a whisper from another age, there's only one thing left to say. Good night, traveler. Even if this time you stayed fully awake.